Okay. Hello, everyone. My name is Fehmi Ekin Giritlioğlu. You can call me Ekin or anything you want. I am a Goals 2024 participant, uh, and I'm a PhD student under Brent Nelson. I'm going into my third year this summer. Today, I'll be talking about projections, equivalence of projections, and I'd like to thank the organizers for letting me talk about projections in front of the participants. So feel free to interrupt me at any time and ask questions or wait until the end of the lecture. So let M be a von Neumann algebra in bounded operators on a given Hilbert space, which we'll denote by H. Let P of M be the collection of all projections in M. So when referring to all these projections, I'll use the notation P of M. For any given subset on our Hilbert space S, Hilbert space H, we'll call the subset H, we will write square bracket S for the projection onto the closed span of all the elements in S. So if you take any subset, take this linear span, you'll have a linear subspace. And once you close it up, you'll have a closed linear subspace. And now you can project onto it. The projection onto that space will give you an element, which might give you an element in the von Neumann algebra. It'll be a projection in B of H. So we will now move towards defining an infimum and supremum for an arbitrary collection of projections. Now, if you remember back to lemma 1.2.5, we have that a projection P onto K, a closed linear subspace of H, is in the commutant of M if and only if K is reducing for M. What does that mean? That means that for all elements in the von Neumann algebra, K under X will still sit inside K. And normally we would say this is invariant, but since M is star closed, this will hold for X star as well. So we can say reducing. Now, if we use the bicommutant theorem here, we get that P is in the von Neumann algebra if and only if for all X in the commutant, PH under X is still under PH. So this is a characterization of when a projection is in the von Neumann algebra using the commutant and reducing subspaces. Now notice, given any collection of projections in our von Neumann algebra, for all X in the commutant, XPH will live inside PH because I can just move this X around. Let's see if my pen is working. Doesn't seem to be. So I can move X to the right. XH will still be in H. So XPH, of course, is a subset of PH. Hence, I can take a intersection on both sides on a collection. This gives us the intersection index under this collection will lie inside the intersection on the right side. But notice I can take this X out, possibly making the set smaller. Now this, if this lets me draw, this is basically one note lets me draw. It's not letting me. Okay, this is basically F of an intersection of sets will be larger than X, the intersection of sets. So let me draw. What we're using here is this. So if you have collection, this will contain this right here. Moving on, we can take the span of both these sides, and that gives us that the span of the set right here is contained inside the set on the right. And then notice I can take this x out. X is a linear operator, so the set will not change. Now I can take closures of both sides. Since x is a bounded operator, using continuity, we can say that this subset also doesn't change. And I can take this closure inside. So initially we start outside, but since x is continuous, I could put that inside here. We have that x of this closure span is contained inside this subspace. Now, you see, this is a subspace. This is also a closed subspace, which is reducing, since this is true for any x, we get that this subspace right here is reducing for the commutant. Now, what does being reducing to the commutant mean? That means that we are in the von Neumann algebra M. Why did we do this? We did this to show that if we define this subspace, projection onto this subspace as the infimum, right here, wedge P, this infimum will be in the von Neumann algebra. Using similar arguments, we can define the supremum as the union of all these subspaces in the collection, taking the closed span, is also an M. Now, we call the first one the infimum and the second one the supremum. Okay. And it is important that they all still lie in M if you initially started with a collection. Now, using positivity, we can obtain a partial ordering on the projections. Basically, P is less than Q if you take Q minus P and still get a positive operator. In fact, if you add to this order structure, this supremum and infimum, we get that the projections with this order is a complete lattice. What this means, and more details, can be found in exercise 4.1.1. However, though, this positivity order is way too rigid for us. Let's look at 2x2 matrices. In 2x2 matrices, let's look at these two matrices, 1, 0, 0, 0, and 0, 0, 0, 1. They're both rank 1 projections. The first one projects to the first coordinate, and the second one projects to the second coordinate. But we can't compare them using the positivity order. They're not comparable. So to compare them, we're going to introduce another ordering in the projections on it. Now, let's talk about subequivalence. For two projections in the von Neumann algebra, we say P is equivalent to Q and write P squiggle Q if there exists a partial isometry V in M such that the source projection of V, V star V, is P, and the range projection of this isometry, V star, is Q. Now, initially, this might look confusing, but what this is saying is that there exists a partial isometry in M sending PH to QH. Basically, this could be thought, this is an isometry between PH and QH if you're strict. And PH perp is being sent to 0 by this partial isometry. Now, this can be thought of as two projections are equivalent in M if their subspaces can be sent to each other isometrically using an isometry in the von Neumann algebra. Okay, now what is subequivalence? We say that P is subequivalent to Q, so P is subequivalent to Q, and writes P, this squiggly thing in the bottom, if there exists a partial isometry V, once again, such that the source projection will be P, however, the range projection will be a projection less than Q. less than or equal than Q. Now what's happening here? V is sending P, the pH, to a subspace of QH. If P is subequivalent to Q, but P is not equivalent to Q, to signify that we can write P just squiggle Q. All right. Notice P is equivalent to Q. Like I said, there's a partial isometry in the von Neumann algebra sending pH to QH and the rest to 0. And moreover, I'm repeating myself here, P is subequivalent to Q means pH is sent to a subspace of QH. And pH perp, V is just sending it to 0. Now, we remark that every time I'm saying with a partial isometry in the von Neumann algebra, M is important. Let's see the subtlety. Let's look at the von Neumann algebra, the collection of matrices A, 0, 0, B for complex entries is a von Neumann algebra. However, these two are not equivalent. I can't send these spaces to each other using a partial isometry that is A, 0, 0, B. However, if I did not have this constraint of A, 0, 0, B, for example, if I was in 2 by 2 matrices, I could do this with the partial isometry 0, 0, 1, 0. If you check, V star V is going to be this first guy, and VV star will be this second guy. That's why it's important sometimes to emphasize that this equivalence is in the von Neumann algebra, and you can write this, and you can express this in notation by saying P squiggle Q with a subscript M. So two projections may not be equivalent in different von Neumann algebras, as mentioned. Now we have a proposition that says that squiggle M, we're calling it an equivalence. I'm quoting Gold's notes here. It will be a crime for notation if this was not an equivalence relation. And it is an equivalence relation, so no crimes here. So let's read it. Squiggle M is an equivalence relation on the projections on M. And the relation, subequivalence, is reflexive and transitive. Now, you can try this yourself, or you can look at the notes. If you have an intuition for what projections to use, what partial isometries to use to witness these transitivities, you are probably correct. What you need to do is to go into details and show that algebraically everything holds. Or you can see notes, of course. Now, proposition 4.1.5 says that for a von Neumann algebra M and two projections in M, if P is subequivalent to Q and Q is subequivalent to P, once again, to avoid crime in notation, they should be equal to each other. Now, this might remind you the Schroeder-Bernstein theorem, which says if you have an injection sending A to B, two sets, and another injection sending B to A, that there is a bijection between them. They have the same cardinality. We're going to use a similar idea, basically steal the proof, but make sure that it works in our linear setting. Now, the technical details are a bit tedious, and the algebraic relations are long, but it is good to go through it, I think. If you want to see the details, you can go check the notes. And in fact, notes refer to exercises to fill in some details they don't give. But I will now convey to you what the idea is. This theorem, the proof in the notes looked daunting to me at first, but after seeing this idea, I feel better about it, and hopefully you'll feel better about it too. Now, suppose we have P subequivalent to Q and Q subequivalent to P. That means we have a projection sending pH to some subspace of QH. So say I have PH here. So this is a space. It's sending it to QH, but just some part of it. Let's call this isometry V. Now, what this means is that V star V is P, and V star is containing Q. Well, V star is projection onto this squiggle. What we also have is another one, same thing, but this time, let me keep the shapes. We have U sending QH to this tiny part. Now, what you can do here is reverse this and notice that what we have is we have U star here sending the squiggle into QH. So how can we use these two maps to produce an honest-to-God isometry? So step one, we start with V. Let's see what V does to pH. Now, if V is somehow able to fill the entirety of QH, we're done. That's a partial isometry from pH to QH. However, in the bad case, we will have this small part laying around. Now, to remedy this small part, let's say, okay, in the small part, I'm going to use U star to possibly get back to somewhere here. So in this green part above the yellow highlight, I'm going to use U star, sending from here to here. Now, let's denote this as P1H. Now, let's cut off P1H and see what's remaining. So this is P minus P1H. And I'm going to use V to send this small part back into this part right here, which is Q minus Q1H. Okay. Now, possibly we might have another gap, right? And this gap right here, you guessed it, I'm going to use U star again. This time, this is going to create P2, Q2. And what is a von Neumann algebra proof if not doing things infinitely many times? We do this infinitely many times, we're going to have P1, P2, P3, Q1, Q2, Q3. And this collection right here will be the sum of all these PIs. However, this P1, P2s, they might not fill the entirety of pH. And that's where we say, okay, let's cut our losses. This last part here is going to be P infinity. The remaining part, that is P minus this entire PI. On this P infinity, we're going to use V, and this V is going to send this P infinity to Q infinity. And all these remaining part on U star. Now, what our claim here is that V is actually, when restricted to here, is a partial isometry from P infinity to Q infinity. There are no gaps. So if we patch U star and V like this, so on this first part, this green part, I'm going to use U star. And on this blue part, I'm going to use V. This should give us an equivalence between P and Q. For the details, I'm going to refer to the notes, and they do everything nice and algebraically, and they're going to use an exercise. So that was, if you have two subequivalent projections, they have to be, so if P is subequivalent to Q, Q is subequivalent to P, they have to be equal with this patching argument. Okay, now using this, let's show something about XH, where X is an element in the von Neumann algebra. So lemma 4.1.6 says, given an element in the von Neumann algebra, projection into XH closure span, same thing, x star h, they both lie in M. So these projections, they don't necessarily have to lie in M a priori, but we're going to prove that they lie in M. And in fact, they are equivalent. So there is a partial isometry in between them. Now, we use theorem 3.1.1, the polar decomposition. If you want a partial isometry to appear out of thin air, best thing to do is polar decomposition. We're going to use this partial isometry. And one caveat is that this partial isometry, has to live inside M for me to be able to put M under this squiggle. So luckily, however, the polar decomposition guarantees that this partial isometry lies in M. Now, the corollary after the polar decomposition says that the polar decomposition of X star actually uses V star. Now, if you go inside the proof of 3.1.1, we will see that the range projection of V is actually XH square bracket. And using the same thing, but this time on X star, it's going to swap everything, swap V to V star, and give us that the source projection of V is actually X star H. And immediately, this gives us the result. So given anything in a monomial algebra, its range, when you close it up, when you project onto it, you're still going to be in a monomial algebra. Okay. Now, let's talk about a great proof tool when working with projections, the central support. I'm checking how I'm doing on time. Okay. For X in the monomial algebra, the central support of X in M is the following projection. It is the infimum of all central projections that satisfy this equality. So when you do xz and zx, I should still be getting x. You may want to write, we're taking these projections in the center of M. So if you want to emphasize this, you can just add a subscript M. Now, instead of taking arbitrary elements, let's look at projections. What is the central support of a projection? So we say two projections are centrally orthogonal if their central supports are orthogonal. That is, ZP times ZQ is 0. How are we able to write this? We're able to write this because ZP and ZQ are also central, and hence they commute. They're in the center. So when you have two projections commuting, to check that they're orthogonal, you can do this. Okay, now notice ZP is equal to P implies that the projection Z is larger than P. If applying on the left by projection is not doing anything, then your projection should be bigger. And hence, the central support of P is a projection that is larger than P in the positivity order. So you can think of the central projection of a projection as the smallest central projection that is larger than P. Once again, the central support of P is a central projection that is the smallest central projection that is larger than P. Now, since these central supports are bigger than the projections, if you have two centrally orthogonal projections, they necessarily have to be orthogonal. Now, another way to think about and use in proofs about the central support is that the central support of a projection is the supremum of xph for all elements x in the von Neumann algebra. And this is going to equal this here, mph. Now, the second equality is the definition of MPH. So let Z be this right here. We only have to prove the first equality. And what are equalities in analysis? There are two inequalities. So let's do that. But first, no, never mind. Now, since for every element, sorry, I skipped a line. Let Z be this square bracket of MPH. Since the identity elements, all von Neumann algebras are unital, that's how we define them. Since the identity is in M, if you stick identity here, you will see that P is contained in Z. Sorry, P is less than Z in the positivity order. Now, since X in the, given any X in the commutator of M, X MPH, I can move X is commuting with everything, and XH will be less than H, a subset of H. So we get that MPH contains X MPH. So we get that when you close it up, that's going to be reducing for M commutator by the continuity of X, since X is bound. So taking expands is not bad. So now MPH, the span of MPH is definitely reducing for M. If you stick an X here, this M is going to absorb it. So we get that the Z is both in M and M commutant. Well, the intersection of these is the center. So Z is in the center. It's a central projection. Thus, the central support of P will be contained in Z. Okay. Now, conversely, for any element in the von Neumann algebra, we can write XPH. We can stick ZP here because let me remember why we can do that. Yes, ZP is larger than P. Since ZP is larger than P, we can put ZP right here. But ZP is in the center, so it's going to commute with X. So we can move ZP from here to here. And thus, we have found that XPH, if we look here, we see that the closed span of XPH projection is going to be less than this guy right here, because putting this guy on the left did not change anything. And then, since this holds for all X, we get that Z is less than ZP. Remember, Z was the collection of all of them, and if every single one of them is larger than it, smaller than it, then Z is also going to be smaller than the central support. Okay. Now we have this guy is in the positivity order less than Z, and Z is also in the positivity order less than the central support of P. Therefore, they have to be the same. And that completes the proof. Now, proposition 4.1.9 says that if M is a von Neumann algebra, for two projections, the following are equivalent. So a nice characterization of being centrally orthogonal. P and Q are centrally orthogonal. P and Q is a zero operator. Interesting. And there does not exist projections strictly larger than zero. So they have to be two projections that are strictly larger than zero. P0 and Q0, respectively less than P and Q, such that they're equivalent. So I could not be able to find two smaller projections that are somehow equivalent. I'm going to leave the technical proof to the notes in the interest of time and continue. But we're going to use this third part nicely. This third characterization. Now, lemma 4.1.10 says that if you have two families, pairwise orthogonal families, such that each pi is orthogonal to qi, each pi is less than qi, so you have an orthogonal family, pi right here and qi right here. If this guy somehow lands inside here, this entire family, when you sum pi and then sum qi, this relation will still hold for their sums. So if you have a family such that pi is less than qi, orthogonal families, then these sums hold as such. In particular, if you have that each are equivalent, then their sums will also be equivalent. Now, how do we prove this? If you have an inkling on how to prove this, is probably correct. Let's look at all these single projections, all these single partial isometries that witness pi is less than qi. Let's name it ui. When you patch all these ui's up, it's just going to give you the partial isometry between the big sums. And I'm going to leave the details to the notes on how this is working, algebraic details. And the last assertion that if everything is additionally equivalent, the sums will also be equivalent, follows from 4.1.5, the Schroeder-Bernstein thing, where if you had P is subequivalent to Q and Q is subequivalent to P, you can combine them to obtain equivalence. It's just an application of that. And now for a nice big theorem, the comparison theorem. In A1 Neumann algebra, if you have two projections, then there exists a central projection, that means a projection in the center, such that when you restrict to that part of the space, or should I say, if you stick z on the right, let's say, then I am now able to compare them. And I'm still able to compare them when you stick 1 minus z into them. So how do we prove this? We prove this by utilizing the third characterization in our central orthogonal characterization. So let's create a family of such P zeros and Q zeros. So by Zorn's lemma, there will exist maximal orthogonal families of maximal families of pairwise orthogonal projections, such that for all I, Pi and Qi are equivalent. And let's define P0 to be the sum of all these Pi and Q0 to be the sum of all these Qi. So P0 is possibly a smaller projection than P, and Q0 possibly a smaller projection than Q, that are equivalent to each other because all their pieces were. And using the previous proposition, they'll still be equivalent. Previous lemma, sorry. And then, since the families are maximal, I should not be able to find on the remaining parts of P and Q two projections that are equivalent to each other. Then I could just add them to the family and gain something bigger in the Zorn's lemma order. Now, if I can't do this using my characterization of central orthogonality, I can immediately say that the central support, these two projections are centrally orthogonal. Now, how do we utilize this? Let's denote the central support of Q minus Q0 as Z. This gives us that, you remember if two projections have orthogonal central supports, if they're centrally orthogonal, then the multiplication of their central supports is 0. Now, the central support of P minus P0 is a larger projection than P minus P0. So this statement implies that I can remove that Z. Or if I do the algebra, send the negative part to the right, I get that PZ is equal to P0Z, is equal to P0Z. Not equal, they're the same, and hence equal. Now, if a partial isometry witnesses the equivalence of P0 and Q0, then we're going to have that P0Z is equivalent to Q0Z with BZ, which is restrict our partial isometry to the space of Z. Thus, PZ, which is equal to P0Z, is equivalent to Q0Z, which is less than QZ. So what do we have here? We have compared this and this. So this gives us that PZ is less than subequivalent to QZ, my bad. Now, similarly, you can show that P01 minus Z is equivalent to Q01 minus Z. And since Q minus Q0 is less than the central support of this itself, which is Z, we then have that this guy right here is subequivalent to this guy right here, which is exactly what we wanted. So PZ QZ, Q1 minus Z, P1 minus Z, PZ QZ, Q1 minus Z, P1 minus Z. So let's look at this theorem again. This is saying that give me any projection, there has to be somewhere I can compare them. All right. Now, what if I don't have any central projections or any non-trivial central projections? If my von Neumann algebra is a factor, the only central projections I have are 0 and 1. So let's see what this theorem gives us then. Let M, so a quick corollary, let M be a von Neumann algebra as a factor. Then for two projections, PQ and M, exactly one of the following holds. P is strictly, I don't know how to say this. P is less than Q, but not equivalent to Q. P is subequivalent, but not equivalent to Q. P is equivalent to Q, or Q is subequivalent, but not equivalent. Strictly subequivalent. Let's say P is strictly subequivalent to Q, or P is equivalent to Q, or Q is strictly subequivalent to P. Only one can hold. And why is that? We just plug in all the different possibilities. So what are my central projections? They are 0 and 1. So if PZ is less than QZ, and this only holds for Z equals 0, then Q is strictly less than P. So if you go back to our theorem, when can this theorem hold? There has to be a central projection satisfying this, so it can work for 0 or 1. So I have three cases. It works only for 0, it works only for 1, or it works for both. Now, if it works for only one of them, you get strict subequivalence, and which one is bigger depends on which one holds. And if it holds for both of them, then they're equivalent. And in here, we use the fact that this and subequivalent gives you Q is equal to. All right. Now let's talk about compressions. For a von Neumann algebra M in bounded operators on H, if P, not necessarily in the von Neumann algebra, in B of H, is a projection, we define P and P to be all operators, the collection of all operators. There doesn't necessarily have to be a lot of structure. The collection PXP for all X in the von Neumann algebra. We call this a compression or a corner of M. Now, why are we calling this a corner? This terminology comes from the fact that when we identify H as PH direct sum 1 minus PH, we can represent PXP as this square matrix in the space bounded operators on PH direct sum 1 minus PH. Becomes this corner right here. Now in here, we're viewing PXP as an operator PH. In fact, for the special case, when your von Neumann algebra is bounded operators on H, any single projection, the corner gives you bounded operators on PH. So let's say you have 2 by 2 matrices. If you take, okay, let's say 3 by 3 matrices. If you take a rank 2 projection, the corner is going to give you 2 by 2 matrices. Now, let's notice what kind of structure we have on P and P. It is a subspace, a linear subspace, and it is closed under taking adjoints. Let's see, so PXP adjoint is PX star P, so we're fine there. Projections are self-adjoint. Now, there are actually two cases where P and P is a star algebra. The first is when P is inside the von Neumann algebra, where one gets a star subalgebra of M, and honest Gauss subalgebra. And the second case is when you take P from the commutant, where P and P, I can send this P here, and P squared is P, and I get MP. In both cases, P becomes the unit of the star subalgebra. So if P is less than 1, strictly less than 1, we can't get a von Neumann algebra. Remember, von Neumann algebras have to contain the unit of the underlying Hilbert space. However, we can view these algebras as operators on PH, and suddenly I have a unit. Let's see what happens. Now, theorem 4.2.2 says that let M be a von Neumann algebra on bounded operators on H, and P be a projection in the von Neumann algebra. Then the corner P and P and M commutant P, we haven't talked about M commutant P yet. They're both von Neumann algebras in bounded operators on PH, and they are commutants of each other. I'm going to leave the technical details to the notes here. But turns out P and P and, this guy's actually P or P are commutants of each other. Now, let's use this to get a corollary. Corollary 4.2.3 says that if M is a von Neumann algebra, we have a projection inside. If M is a factor, then P and M commutant P are also factors. Interesting. Now, by the previous theorem, they are commutants of each other. So they have the same center. So, both their centers are M commutant, M intersection, M commutant. Now, it suffices to show that M commutant P is a factor. Now, let's do a small inside lemma in the proof. Given any element in the commutant, any operator in commutant, if Yp is 0, remember we fixed a projection P, then actually we're going to have for all X and M, for all Xc in H, Yx P Xc will be Xy P Xc. Remember, they commute. It's going to be a 0. And then since M is a factor, okay, so this is our small lemma here. Oh, wait, sorry. our small lemma hasn't ended. We just have that yxp is 0 given any x and c. Now, since m is a factor, the only central projections we have are 0 and 1. Hence, mph, which is equal to the central support of p, is 1. This means that mph is dense in H. Now, mph is dense, so this guy right here is dense in H. And in a dense set, our operator is giving us 0. So the above implies that y has to be 0. Now, this is interesting. We have just any element in the commutant. If for a projection you're giving 0, you have to be 0. And that this is 0, then you have to be 0. Now, if zp, for some z in the commutant, is in the center of m commutant p, then for all y in the commutant, we're going to have zy minus yz. So what we're looking at is elements in m commutant p. Now, if this guy is in the center, if I have an element in it, we picked an arbitrary element in the center of m commutant p here. Now, if z, Now let's look at what happens when we look at zy minus yz. We're checking if z is in the center of the commutant initially. We just know that it's an element of the commutant, but we don't know that if it lies in the center. Now we're going to show it in fact does. Now zy minus yz, when we expand it out, get these p's here. Now p commutes with y, so we can send this guy right here. What we also have is that zp is in the center, so I can send this guy here. We get that zpy what's going on here is that I'm able to move this zp here. Okay. Right, I'm not able to move that CP there yet. But what I can do here is see that yzp is equal to ypzp. And now I can move it to be like this, yp. And zyp should also be equal to zpyp somehow. Yes, because y commutes with p. So this is zyp squared, which is equal to zpyp. So we still get 0. Now, all that to say, sorry for algebra error, all that to say, we get that yz minus yp, sorry, yz minus yzp becomes 0. And if you use our previous lemma here, if you have something in the commutant p is equal to 0, which is exactly what we have here, then the first guy has to be 0. Now, if zy minus yz is 0, that means z commutes with y. Now, y is arbitrary, so we have to have that z is in the center of the commutanon of M. However, the commutanon of M is a factor because M is a factor. Their centers are the same. Z has to be a multiple of the identity, and hence ZP is going to be complex numbers times P. Thus, the center of M commutant P is C times P, and therefore M commutant P is a factor. So what did we show? We show that if M is a factor and you have some projection, PMP and M commutant P are both factors. Okay. Now this next proposition says that the compression, the Neumann algebra that comes out of the compression, depends only on the equivalence class of P in M. So let M be a Neumann algebra in B of H, P, Q, two projections that are equivalent in M. This is important. It has to be equivalent in M. Then PMP and QMP, QMQ, the corners are spatially isomorphic. Now, to get the spatial isomorphism, we need an isometry, but we have a great candidate, which is the partial isometry that realizes the equivalence of P and Q. This V as an isometry from PH to QH implements the spatial isomorphism. And for the details, I'm going to refer you to the notes. Once again, the corner depends only on the equivalence class in squiggle of our projection. So now let's talk about minimal and abelian projections. Let M be a Neumann algebra. We say a projection is minimal in M if P is non-zero and PMP is just complex numbers times P. Now we say that P is abelian in M if PMP is abelian. Let's see some examples. So if you want to say this shortly, P is minimal if the corner is complex numbers, and P is abelian if its corner is abelian. Okay, now an example. Let's say we have any projection in the von Neumann algebra. We have remarked that the corner is going to be boundary operators on PH. Therefore, to be abelian or minimal, P has to be rank 1. The only abelian B of something is B of complex numbers, so you have to be rank 1. Now, example 2 is an abelian example. Now, let X mu be a sigma finite measure space. Recall that an F is a projection in L infinity if and only if it's a characteristic function for some measurable set E in X. This is exercise 1.2.3. Now, consequently, all corners are of the form L infinity of E mu restricted to that E for some measurable E. Thus, all projections in L infinity are abelian. However, to be minimal, we have to have that E is what we call an atom. In fact, this is a characterization. For details, see exercise 4.2.3. An example of an atom would be a single point with mass 1, for example. Now, if P is minimal in M, for Q, another projection such that it's less than P, we have that Q will be PQP. So adding from the right and left, multiplying from the right and left by a bigger projection is not going to change anything. That's going to lie in P and P. However, that since P was minimal, that corner is just CP. Therefore, either Q is P or 0. Consequently, if P is a projection such that Conversely, say we don't know that P is minimal, but we have this characteristic that any smaller thing is P. There's nothing strictly smaller other than 0. Then, since PMP is a C-star algebra generated by its projections, which are just 0, 0, and P, we get that PMP is going to be C times P. Thus, P is minimal. So this statement that Q lies in the set 0P whenever Q is a projection that satisfies Q is less than P is an equivalent definition of minimality. Now, since corners depend on only the equivalence clause of a projection, if P is minimal, then, or respectively abelian, then anything equivalent to it will also be minimal or abelian. In fact, we can pass to subequivalent projections. If P is minimal, Q is subequivalent to P implies Q is equivalent to P. So because there's nothing smaller than P, the only thing you can be equivalent to is P. Therefore, Q has to be equivalent to P. Therefore, Q is also minimal. Now, if P is abelian and Q is subequivalent to P, let's take our partial isometry that implements this. Then QMQ is going to be isomorphic to VV star M VV star, which is contained in PMP. Now, PMP is an abelian monomial algebra, so anything contained in that will also be an abelian symbol. Will also be abelian. Thus, to record this, we have proposition 4.2.7. If you have two projections in M such that Q is subequivalent to P, if P is minimal, respectively abelian, Q also remembers it. Q is also minimal, respectively abelian. Now going really fast because 3 minutes remaining. Now we have a theorem, 4.2.8, which says using these minimal and abelian ideas, let M be a monomial algebra and another monomial algebra on another Hilbert space K. If pi is a normal unital star homomorphism, then pi of M, so the image of M under pi, is going to be a monomial algebra. Now, I said unital, so we have the unit. Now, it is going to be a monomial algebra. I'm going to leave the proof to the notes. All the technical details are there. And remark 4.2.9 is that this actually has a converse, a partial converse. The star isomorphisms between monomial algebras, so instead of n here, if you just look at pi of m, so m to pi of n, star isomorphisms between monomial algebras are automatically normal. Interesting. The proof of this is very technical, and the book referred to in the notes is Operator Algebras, Theory of C-star Algebras and Monomial Algebras by Bruce Blackadar, section 3.2.2. But if you want to see what the argument that is being relied on, it is there in the notes, if you want to see just a crucial algebraic idea. Now, once again, if you have a star isomorphism, you don't need to check if that is continuous. You automatically get that it is sigma weak operator topology continuous. It's automatically normal. And that is it for this lecture. Thank you for listening. I'm going to stop recording.